containing A, where A is a point in Rn, such that f prime A, this is Jacobian of f at A. So this is n cross n matrix of the. This is basically the matrix representation of df, the derivative of f at the point A with respect to the standard order basis of Rn. So this is the second assumption. Determinant of this is not equal to 0. That is, the derivative of f at the point A is invertible. Okay, so this is the first assumption on f, continuously differentiable, and this is the second assumption. The derivative of f at A is invertible. Then there exist open sets U, open set where in Rn, and the second open set is denoted by W. W is also open set in Rn, containing, so U contains A and W contains f of A. So A belongs to U and f of A belongs to W, such that following happens: f of U equal to W and f is injective. That is to say, the restricted function of f on U from U to W is bijective. Injective and surjective, that is invertible. And second, if H from W to U is the inverse of, if is H is the inverse of f restricted on U, then H is also continuously differentiable on W. On W, and third item gives the expression of the derivative of the inverse function for all y in W. The derivative of H at y, this is equal to derivative of f at the point H y and inverse of that. Okay. So now we prove this theorem. So next page is page number 4. So proof of inverse function theorem. So first we simplify the statement, simplification. if first let t equal to derivative of f at the point A. Okay, then this is a linear transformation Rn to Rn, and by given condition t is invertible. Okay, that is T inverse exists. Now consider T inverse composed with f. This is again a function from Rn to Rn, so that a derivative of T inverse composed with f at the point A, this is equal to identity by chain rule. Okay. Now note that not one, so inverse function theorem holds for f if and only if inverse function theorem holds for T inverse of f. Okay, T inverse composed with f. So let's write. So inverse function theorem holds true for if and only if it holds, it means inverse function theorem holds true for T inverse composed with f. So in the light of this note 1, we assume that, therefore we assume that the derivative of f t equal to identity. Okay. Now second step is finding. So this is step 1, simplification, and step 2, finding open neighborhoods u and w. So u neighborhood of open neighborhood of little a, and w is open neighborhood of f of little a, such that f of u equal to w, and the restriction function f restricted on u from u to w is invertible. Okay, so such so in this step we will find such open neighborhoods u and w. Okay, so first note that for h in Rn, if f of a plus h minus f of a equal to 0, that is f of a plus h equal to f of a. So if this happens, then f of a plus h minus f of a minus t times h. Now t is identity, so t of h equal to again identity over norm h. So norm of the numerator also. So this is equal to so f of a plus h equal to f of a. So this is equal to norm of h over norm of h equal to 1. So but limit h tends to 0, f of a plus h minus f of a minus t h, norm of this over norm of h, this is equal to 0 by the definition of derivative. Next page is page number 5. So therefore there exists an open neighborhood. So without loss of generality, we can consider that neighborhood as convex. So this implies there exists V open plus convex in Rn containing the point A, such that such that f of a not equal to f of x for all x belongs to for all x belongs to V set minus singleton set A. Okay, so suppose this is without loss of generality, one can consider uh, some small ball with center at A and some small radius, so this is suppose V, and this is what, so equivalently f of A, so this is basically f of A not equal to f of A plus h. Okay, for all h belongs to R n minus 0 non-zero h with A plus h in V. Okay, so furthermore, we may choose V small enough so that determinant of derivative of f at x, this is not equal to 0 for all x in V, and okay, so we may choose V closer minus A and A plus H, this is V closer. Okay, so and second condition D J f I, the derivative of the function f at x minus derivative of, so jth partial derivative of f I, ith component function of f at A, this has absolute value less than 1 over 2n square for all x belongs to V. So we'll so here we have note 2. We can choose such V because we can, because f is continuously differentiable around A. Okay, we can choose such V as f is continuously differentiable around A, so that is in an open neighborhood of A. Now we claim, this is claim 1. So now we claim that f is injective on V. Okay, now proof of claim 1. So first we prove that f is injective on V. So we define g of x equal to f of x minus x. Okay, then dg, the derivative of g at x, this is equal to derivative of f at A minus identity. Okay, and this is equal to derivative of f at A, so not A, this is x minus t is identity, so this is t. So this is equal to derivative of f at x minus derivative of f at a. So derivative of f at a equal to t, and that is equal to identity. And well, now this implies jth partial derivative of ith component function of g at the point x. Okay, and absolute value of this is equal to basically the jth partial derivative of ith component function of f at x minus dj f fi at a, and absolute value of this. Now from this condition 2, this is less than 1 over 2n square. Okay, so this is less than 2n square for all x belongs to v. So by condition 2. Okay, so now next page is page number 6. Now for x and y in V, what we have, so by triangle inequality, this is norm of x minus y minus norm of f y. So better write norm of y minus, so let me write again, norm of y minus x minus norm of f y minus f of x, and this is less or equal to norm of y minus x minus f of, so put bracket f of y minus f of x and close bracket. Okay, and this is equal to basically g of g of y minus g of x, and so this is bounded on V. So the partial derivatives of component functions of G, these are bounded above by m equal to 2 over 2n square. So now here we use lemma. So what we have already proved. So by lemma 1, this is less or equal to m equal to 1 over 2n square times m equal to n, and this is n times norm of y minus x using lemma 1. Okay, and from here what we have, this implies so this will be cancel out. So from here, so right hand side, this is equal to norm y minus x over 2. So this implies 1 over 2 norm y minus x less or equal to norm y f of y minus f of x. Okay, and so this implies norm of y minus x less or equal to 2 times norm of f of y minus f of x, and we label this inequality as equation 1. Okay, and this implies if so now if y not equal to x, that is y minus x not equal to 0, then this implies y minus x norm of this greater than 0, and this implies 2 times 2 times f of y minus f of x norm of this is also greater than 0. That means f of y minus f of x not equal to 0 means f of y not equal to f of x. So y not equal to x implies f of y not equal to f of x for all x comma y in V. Okay, this implies f is injective on V. So this proves claim 1. Now claim 1. Now next page number 7. Now note that the boundary of V. So what is this? V closure minus V is open set. So let me draw. This is A and this is V. This is V. Now and this is compact. Okay, and also we have f of x not equal to f of a for all x in the boundary of V. Boundary of V is compact. So this implies there exists some positive real number d such that f of a minus f of x has norm greater than or equal to d for all x belongs to boundary of V. Okay, so suppose here we have suppose this is f of a. Okay, so you can consider d the distance from fa to the boundary. So this is suppose d. Okay. Now we defined w equal to set of all points y in R n such that, so basically we are taking this is w equal to open ball with center at f of a and radius d over 2. So that is y belongs to Rn such that y minus f of a, okay, less than d over 2. So fact fact for all y in, so w, if y is a point on w, then the distance so suppose y is here, so the distance of y from the boundary so this line, this curve, so the distance from y to this curve is always greater than the distance of y from the center fa. Okay. That is norm of y minus f of a. This has norm always strictly less than norm of y minus f of x, and this happens for all x from boundary of V. Okay. So this is basically the image of V under F. So, and inside we take some open neighborhood, small enough open neighborhood W of FA. So this is open neighborhood. So this is, first of all, this is open in Rn, and W contains f of A. So we found W. Now claim 2. So what is claim 2? Given, so for every point in W there exists a unique pre-image of F inside V. So given Y in W, there exists unique X in V such that f of x equal to y. So y has unique image in V. So this is now proof of claim 2. So once we prove claim 2, then we can consider U equal to F inverse of W. Okay. So to prove this claim, we define H function from V closer to R by H of x equal to f of x minus y norm of this square, and one we can write this as summation yi minus f I of x whole square. Summation is over I equal to 1 to n. Okay, so now V closure is compact and H continuous. Therefore, the function H, this implies H admits its minimum on V closure. So the minimum, that is, there exists some x such that h of x is less or equal to h of x prime for every x prime in V closure. So the minimum can occur either in the interior or on the boundary. Okay, and inequality. So okay, so let us label this inequality by equation 2. Now it follows from inequality. So you know, from so for every boundary point we have y norm of y minus fa. Okay, so for A belongs to V closure, of course, and for every boundary point x, we have norm of fx minus y. This is strictly less than y minus f of a. Particularly for A, we in the interior point we have. So this is page number. Page number 17. This is page number 8. Okay, so by equation by equation 2 we have the minimum of H does not occur on boundary. Boundary of V. Therefore, it is in the interior of V. Therefore, it is on the interior of V. In the interior of V, let say at X belongs to V. Okay, so H has maximum or extremum, in particular maximum. So H has maximum at X. So derivative of H, so every partial derivative of H at X equal to 0, and the jth partial derivative of H at X, this is equal to 2. So H of X, this is equal to y minus f of X norm of this square. Okay, so H, the jth partial derivative of X, H at X equal to so, and this is equal to summation y minus f I of X whole square, summation over I equal to 1 to n, and this is this is equal to minus f I of X, then summation I equal to 1 to n times dj, jth partial derivative of ith component function f I at X. So this is equal to 0, and this, so for all j lies between 1 and n. Okay, and this implies the derivative of f at X acting on y minus f of X, this is equal to 0, and you know, for every X, for all X in V, determine so df at X, this is from Rn to Rn, this is invertible. Okay, so this is injective. So this implies y minus f of X equal to 0. This implies y equal to f of X. So this proves claim 2. So now we are about to finish the proof. Now define the measure of the work of the proof is done. So we define V intersection with F inverse of W. This is equal to U. Then by construction, F restricted on U to W is 1 1 and 1 2, that is, and hence invertible. Next is page number 9. Now finally we have to show continuity of of F inverse and differentiability of F inverse. Okay, let y1 and y2 are points in W such that F inverse of y1 x1 equal to f of f inverse of y1 and x2 equal to f inverse of y2. Okay, so here this is restricted function, f restricted on u, and f inverse is f inverse of f restricted on u. Okay, so by inequality 1, we have, so these are points in u which is equal to v intersection with f inverse of w. So in particular x1 and x2, they are points in v. So x1 minus x2, so inequality 1 implies norm of x1 minus x2. Okay, this is less or equal to 2 times f of x1 minus f of x2. Okay, so for every, so this implies f inverse of y1 minus f inverse of y2 as norm less or equal to 2 times y1 minus norm of y1 minus y2, and therefore this is Lipschitz function. This implies f inverse is continuous on W. Now the last thing to show differentiability of f inverse on W. So this is the final step. Let x belongs to u, comma a equal to df at derivative of f at x, and y equal to f of x. This belongs to W. Okay, now define phi of x. This is equal to f of x plus h, as like previous lecture. So phi of x equal to f of x plus h minus f of x minus a of h. So a equal to derivative of f at x. Note that a inverse exists for all x in U. Therefore, by multiplying with A inverse, so star implies A inverse of f a x. Sorry. Okay, let us go to the next page, page 10. Therefore, A inverse of f of x plus h minus f of x, this is equal to A inverse of phi of h minus, so let me, so well this is phi of h. Okay, so here x is fixed. Phi of h minus a of h, and so this is plus. Okay, this is equal to A inverse times A. This is identity, so this is h plus A inverse of phi h, and here let y1 equal to x plus h and y equal to, so f of x plus h, y equal to f of x. Okay, so this implies f inverse of y1 equal to x plus h and f inverse of y equal to x, and this implies h equal to f inverse of y1 minus f inverse of y. Okay, so now this equation implies A inverse of this is y1 minus y equal to f inverse of h, so h equal to f inverse of y1 minus f inverse of y, and A inverse plus A inverse of phi h equal to f inverse of y1 minus f inverse of y. Okay, so this implies f inverse of y1 minus f inverse of y minus A inverse of y1 minus y, and norm of this, so this minus A inverse of y1 minus y, this is equal to norm of A inverse of phi of f inverse y1 minus f inverse of y, and norm of this. Okay, so this implies limit f inverse of y1 minus f inverse of y minus A inverse of y1 minus y, norm of this over norm of y1 minus y as limit y1 tends to y. This is equal to limit so we may take A inverse norm A inverse outside times limit h tends to 0, norm of phi f inverse of y1 minus f inverse of y. Okay, norm of this over norm of y1 minus y, as okay, so here as y1 tends to y, and this is less or equal to, as we have taken a norm of A inverse out. So well, and by equation 1, this is less than so well, this is now this is equals to, so right hand side equals to norm of A inverse times limit y1 tends to y, norm of phi f inverse of y1 minus, so here single bracket f inverse of y, norm of this over f inverse of y1 minus f inverse of y, norm of this, times f inverse of y minus f inverse. So this is y1, f inverse of y, norm of this over norm of y1 minus y. Okay, this quantity is less or equal to 2. So next page 11. So therefore we have norm of, so limit y1 tends to y. So left hand side is norm f inverse of y1 minus f inverse of y minus a inverse of y1 minus y, norm of this over norm of y1 minus y. This is less or equal to 2 times norm of a inverse times limit y1 tends to y times phi, norm of phi f inverse of y1 minus f inverse of y, norm of this over norm of y1 minus y, and as well, so this, so f inverse, and this is equal to 0. So this implies f inverse is differentiable at y, and derivative of f inverse at y equal to a inverse. And what is a inverse? Derivative of, so what is a derivative of f at the point x equal to f inverse of y and inverse of this. So this is equal to a and inverse of this. So thus inverse function theorem is proved. Okay, so let us stop here. Thank you.